my agenda. And the first one is a parking procedure. So in this audience, I'm sure we'll love a parking procedure. That's the hope. The second thing is the Schubert positivity question that we are aiming to address. So we've been thinking about this question for a good 3-4 years now, and I blame Alex Wu for getting us hooked onto this question. And then third thing is I'll give you a new basis for the polynomial ring. And finally, I'll talk about a correspondence on words akin to Robinson, Shenstedt, Knuth. Okay. Right. So here's the parking procedure that I have. So if you've seen parking functions before, grand. Otherwise, let's just take this at face value. I have parking spots which are indexed by the integers. So I've got infinite parking space, and I have n cars, and each car has a preference for a spot. Okay, so cars want to park in their preferred spots. And so here's a generic picture after, let's say, k cars have parked. Each, so the occupied spots decompose into maximal intervals. So those I'm calling I1 through IL. And then every interval is, so this is where I start to deviate from the usual parking business. Every interval has one distinguished spot. Okay, so this is the marked spot. So here below, you see a generic case where the reds are the cars, more like the wheels, and the blue are the marked spots in that interval. Okay, so here's the process. Once k cars have parked, the k+1th car comes in. It starts out at negative infinity, and it probes for a position to park. If a spot is free, it takes it. Otherwise, the spot is taken. But if it's taken, then it belongs to a maximal interval of occupied spots. And then it has to make a choice, right? So this is where usual parking procedure deviates. I compare my preference with the marked spot in that interval. If I have crossed the marked spot, I will keep going to the right endpoint and park at the next free spot. If I haven't crossed the marked spot, I reverse the vehicle and I traverse in the opposite direction and I park to the left. Okay. And then finally, the last spot that you park in becomes the unique marked spot in the interval wherever you parked. Okay, so the marked spots can keep moving around as the procedure, as we go along with the procedure. Okay, so I'll do an example. So here's a word with 6 letters, word of length 6. I'm going to read this right to left. These entries should be taken to be the preferences of the cars. Okay, so right to left, because I'm going to be doing this procedure for reduced words, and I multiply reduced words right to left as well. Okay, so that's the first card that comes in. Its preferences for spot 5. Everything's free for the moment. So there we are. It becomes the unique marked spot in its interval. Card 2 prefers spot 1, far enough. 2 marked spots, 2 disjoint intervals. Okay, card 4 also has a free spot. It takes it. But notice now that the marked spot has moved. Because the interval's grown, you managed to attach yourself to a previous interval. So the interval grew and then your unique marked spot moves. That's the 2 moving the marked spot. And then there's another 2 coming. So this here is the 2 that is oncoming, but its spot is taken. So it compares itself with the marked spot, which is also 2, hence it goes right. Okay, and becomes the new marked spot. And now the 3 comes, compares itself with the marked spot, and that's that. Okay, so this is the parking procedure that I'm intending to discuss. And now I can define what I call Coxeter-Sylvester parking words. And a word is Coxeter-Sylvester parking word, CS parking word for short, if the cars end up occupying the spots 1 through n. Okay, so this word here, you see that the spots 1 through 6 were taken, so that's Coxeter-Sylvester. And okay, and so here are the CS Spartan words for lengths up to 3, and you can compute these cardinalities and see that you have the same number of Cocker-Sylvester Parkin words as the usual Parkin functions. And this shouldn't be a surprise, right? If you know Pollack's argument for counting Parkin functions, you realize it happens on a circle. On a circle, the choices of left and right are anti-clockwise versus clockwise, but anything that you can reach clockwise on a circle, you can reach anti-clockwise. So the entire argument works just fine. Okay, and any questions before I proceed? Okay, I'll take that as a no, because I can't see anyone. Right, so here's the question. What's up with this contrived Parkin procedure? Short answer, practically no good. Long answer, we came up with this because we wanted to answer this question that I'm about to tell you next. Okay. Oh, so that's just complete flag varieties. Remember what a complete flag variety is. It's a nested sequence of spaces where dimension of fj is j. Okay. And I will be doing some cohomological computations. So if cohomology and geometry is not your forte, then there's a result of Borel that tells you you could work in a polynomial ring modulo an ideal, and you would be doing cohomological computations secretly, right? So here's the ideal. It's the ideal generated by the elementary symmetric polynomials in n variables. And then Borel tells me the cohomology ring of the complete flag variety is better or easier to work with for us if you work with the polynomial ring and quotient by the ideal of symmetric polynomials. Okay, so famous coinvariant algebra appearing here. And the variety I am interested in is the permutahedral variety. It's a smooth toric variety and dimension n-1. And here's a realization. Pick a diagonal matrix, distinct entries, and then take flags which happen to have this inclusion condition. Okay. So some inclusion condition, it's really determined by a Hessenberg function. So this is a particular regular semi-simple Hessenberg variety. Okay, and as a toric variety, it has a fan and a polytope attached to it, and the polytope attached is well, the permutahedron, hence the name. Okay, right. So let me now get to my actual question. So Anderson Timachko identified the class of the permutahedral variety inside the quotient, the coinvariant algebra. And it's given by this van der Monde-like determinant. And then the task that I'm interested in is expand this as a sum of Schubert polynomials with some coefficients. Right? So on the one hand, you recognize the left-hand side as a specialization of a double Schubert polynomial. But when you expand them, you get products of Schubert polynomials, and multiplying Schubert polynomials is not that easy. So this is not exactly a trivial query. So I'm interested in these A sub W's. They are guaranteed to be non-negative integers because they are intersection numbers. Hence, the combinatorialist might be interested in being able to compute them. Okay, so here's the first answer that we had in maybe a couple of years ago. The computation can be rewritten as this symmetrization procedure. So I call this divided symmetrization. The Schubert polynomial is the input. I have to divide, so it's a rational function, and then I average the rational function over the symmetric group. And for polynomials of degree n-1, I get scalars in the ground field. So that is an honest, rational, or complex number, if you will. Turns out you can encode all of this computation by working in a smaller ring. Okay, so this is the SN invariant part of the cohomology ring of the permutahedral variety, and you map the Schubert polynomial, and you get a McDonald's identity-like expression. And you can do a little bit of work. So there's a lot of action happening here. But long story short, you can express the A sub W's as certain linear combinations of mixed volumes of Minkowski sums of mixed volumes of hypersimplices. Okay, and the index set is reduced words. So this really feels like McDonald's identity, except you have what are called mixed Eulerian numbers. Okay. Right, so it's a nice enough expression, but it shouldn't be really satisfactory, because I told you you're supposed to get non-negative integers. This is rational. It's positive, but it's rational. And it's quite unclear why these numbers would come together and then end up being divisible by n-1 factorial. Okay, so this was the state of affairs a couple of years ago. So we had to figure out how to get around this question. And this is where work of Jean-Christophe Aval and Francois and Dantel comes into the picture. Okay. All right, so let me give you the theorem already. And if I don't get to the end of my talk, at least you take this theorem away. Computing these intersection numbers is taking reduced words and trying to park them. If you're able to park, that's a contribution to a certain structure coefficient. Okay, so for my example, 21543, this has 4 inversions. Here are the 8 reduced words. 4 of them end up being parking words in the Coxeter-Sylvester sense. And hence A sub W is 4. Now this is something that's integral and non-negative, as opposed to positive and rational. Okay, and we need quasisymmetric polynomials to actually arrive at this result. Okay, I'll take a pause here. Questions? All right. Okay. So quick recall. Quasisymmetric polynomials are polynomials with the following property. If you hand me P, I look at the coefficient of x1 to the alpha 1 through xm to the alpha m for a sequence of positive integers alpha 1 through alpha m. This coefficient better equal the coefficient of x sub I1 to the alpha 1 all the way through x sub im to the alpha m for an increasing sequence. So this should be, apologies, this should be strict inequalities. I1 strictly less than I2, so on. And I think Jean-Christophe Aval and Dantel considered this particular ideal first in 2002, and then Francois is on the second paper. Just like the coinvariant algebra, you might be interested in the quasisymmetric coinvariant algebra. And then it turns out that the polynomial ring has this direct sum decomposition where you have the ideal part, and then you have the complement, which ends up being a span of monomials. And the monomials are supposed to remind you, oh, Jesus Christ, man. Okay. Monomials are supposed to remind you, or at least evoke Catalan numbers. Okay, so I'm looking at integer sequences where every suffix, every suffix of length k has a sum of parts less than k. So this is a very Catalan object. Okay. All right. So how does this quotient help us? Turns out that if you take your polynomial and you want to compute its divided symmetrization, you can break it into its good piece, the ABB piece, and you can take it away its bad piece, the piece that lies in the quasisymmetric ideal. Then the symmetrization I was doing over the symmetric group is actually an all ones evaluation of the good piece. So the task becomes to identify the good piece for Schubert polynomials. In other words, I want to reduce Schubert polynomials modulo the quasisymmetric ideal. And if you're hoping for positivity, you're hoping for a positive expansion in the Aval-Bergeron squared basis. And that indeed happens to be the case, though it's not obvious. You have to, it's not immediate if you're just working with the monomial basis in green. Okay, so let me tell you the basis. The basis is indexed by forests, indexed forests, in fact. So what are indexed forests? Well, you have binary trees and the leaves decompose the integer lattice. Okay, so they're going to be disjoint intervals and the leaves are going to be living here and the internal nodes are the internal nodes of the binary tree. For such a forest, I'm going to interpret it as a poset. Okay, strict increases going to the right, weak increases going to the left. And this is where the interval matters. You get inequalities imposed from the interval. Okay, so if you look at the bottom right here, the 6 says the entry in this internal node is strictly less than the 6. So you're getting a flag condition from where your forest sits on top of the integer lattice. And if you move it, well, you get different polynomials. Right? Okay, so here's the definition of a forest polynomial. Bad notation indexed by T sub f is a sum of monomials attached to labelings over all possible forests. So here's an example of a forest polynomial. Okay, so I'm really doing p partitions, except I'm not allowing all labels. My labels are determined by where the forest sits on top of the integer lattice. And as you move the forest, you get more and more polynomials. If you move it far to the right, you will essentially start getting quasisymmetric polynomials. And claim these guys are real good when you try and reduce Schubert modulo quasisymmetric polynomials. Here is something that will help now. Schubert polynomials actually live in the infinite polynomial ring. You can fix a number of variables and reduce the Schubert. Here's what happens. Either you get 0, or you don't need to reduce the Schubert if you're working with the Artin monomial basis. Right? So either 0 or no reduction necessary. Same thing with these forest polynomials. Either 0 if the support is too large. If the blue stuff from before is too large, then your polynomial is inside the quasisymmetric ideal. Otherwise, it doesn't need reduction. And in degree n-1, you notice that you don't need components. You only need honest trees. Those are the only ones that survive. Okay, so this is now the task. I have all of 3 minutes, I presume, or maybe I started 2 minutes late. So let me take a couple of minutes extra if that's okay. So you're tasked with expressing Schuberts in terms of forest polynomials. And long story short, you need a correspondence on words, which will allow you to, I'm trying to mimic the RSK correspondence. You take your word, read it from right to left, and you're going to generate trees. Okay, so I'm going to drop these numbers right to left. You can ask me about the procedure later. And at every stage, I pick up 2 children. Okay, so this is a bottom-up procedure. The nodes come down. So in between the space between 3 and 4, 3s are going to drop. Between 5 and 6, the 5s are going to drop, and you get forests. Okay, so that's my P symbol, and the other one's my Q symbol. So I can take this on any word. So I have a correspondence in words, and the output is trees or forests of the same shape, where one of the forests is a local binary search forest, and the other one's a decreasing forest. Okay. And my correspondence is, I'm going to declare 2 words to be equal if the P symbols match. Okay. And essentially, the P symbols tell you how you can coarsen a known expansion of Schubert polynomials, okay, which runs over reduced words. So here's the coarsening. In the interests of time, let me not dawdle. Yeah, so these 3 reduced words have this indexed forest, P symbol. This single reduced word has this. And here is a case where you get actually a forest with 2 components. So when you reduce modulo quasisymmetric polynomials, this forest with 2 components, this bottom bit, is going to die. Okay? That's the one you will throw out. The other 2 will contribute to the A sub W I was interested in. Okay. All right, so this is pretty much the last slide. Any commutation class is closed under this equivalence. In particular, the set of reduced words decomposes disjointly into these equivalence classes. Each class has an attached forest, its P symbol, the shape, and then the Schuberts decompose as some of these forest polynomials. And when you modulo quotient this by the quasisymmetric ideal, the forests are thrown away, and whatever else survives. Okay. And as a quick remark, for Grassmannians, this correspondence doesn't tell you much. Every reduced word is a class of its own. All trees are linear. This is the same expansion as Schur's into fundamentals. Okay. So here's a bunch of things, but maybe let me not try and push my luck and stop there and thank you.
Thank you. Are there any questions? Well, I have a question. Could you explain how to do the P symbol with the word?
Oh, sure. Yeah, sorry, I decided to. So the idea is I'm going to read the word right to left, and every number is going to drop in this vertically in this space. If you've seen heaps of pieces, I'm doing a heaps of pieces, except I'm building trees. So the 5 falls down the space between 5 and 6 to kind of the lowest place it can fall down to, and there it takes 2 children. Okay, so somehow the parent comes after the progeny here. So the 11 goes here, the 8 goes here, and I guess the 3 goes here. So far, no drama. Everything is able to fall down to the last level. Here's the first time where the 9 would ideally like to sit between the 9 and 10. It can't because this leaf 9 is taken. So it's forced to reside above. And similarly with this 3, I break ties using some rule, which is all the 3s go to the right, the next 3. And then finally this 2. So that's how I get the P symbol. And the Q symbol is recording this growth process. So that's the easy one.
Okay. Well, thank you. Are there any other questions? I see raised hands.
So I can't see anybody. Yeah.
Well, I see there's 2 raised hands, but I don't see their name.
So while you're on this slide, what is the connection between this RS correspondence and the one by Iver-Novelli and Sibon?
Oh, good question. So why the name, right? If you do this procedure, so I think Dari's question, so Dari, let me give one answer and maybe it won't be good enough. So you tell me if it's not good enough. Why am I calling this the CS correspondence? If you apply it to reduced words of Coxeter elements, then this is the Sylvester, the binary search tree construction. So for Coxeter elements, this is the Sylvester correspondence, in fact. So yeah.
So it's like more general?
So so that's the source of the name, that for Coxeter elements, you're really inserting permutations. And for permutations, you're getting binary search trees. Yeah.
I see. Okay.
There's also Alan Knudsen that has a question.
Yeah. So can you say more particularly what the grouping was of the you mentioned Billy Jocker Stanley. So I guess you're saying you have some sort of equivalence relation on reduced compatible sequences.
Correct.
So what is it?
So it's okay. So I'm gonna just rely on the P symbol for the moment, because to actually pin it down, what commutations are possible, it helps to work at the level of trees. So for me, all the 3 reduced words up top give me the same labeled forest, and there was 3 of these, and there are 3 linear extensions to this particular forest. So reduced words are linear extensions is something that I'm relying on here. So I'm essentially breaking the set of reduced words into the set of linear extensions, each set of linear extensions coming from a particular forest poset. So in this case, you get 3 classes coming from 3 different forest posets. So 3 linear extensions here, 1 single linear extension because this is a linear tree, and then 4 linear extensions from this forest with 2 components below. You can actually pin it down and say that, okay, I'm going to allow some commutation if a certain property is satisfied. It's not that pretty. It's not exactly the concise sorts where I say perform this commutation if these letters are the same or something. So it's a little bit of it's a bit verbose, but at the level of trees, it's a little easier. So that's one answer to your question.
If you take ones with in a given grouping, and you see, can you see those terms as the facets of a subword complex? So
Alan, I let me maybe say what I know about these. I haven't looked at some of the subword complex literature. It felt to me, so these forest polynomials are coarser than slides, and they are finer than Schubert's. For slides, you have these slide complexes that Evgeny Smirnov and one more person defined. So I haven't really looked at how the slide complexes come together to decompose this forest polynomial. So that's something I want to stare at further, but I haven't done so yet.
Okay. Well, maybe we can talk about it.
Sure. So one thing, maybe, okay, I probably shouldn't take too much time. Yeah, I'll leave it at that.
And there's a last question from François Bergeron, but make it quick. The next talk's in 3 minutes.
Yeah. So essentially, it's a simple question. Is this doing reduction modulo the Grosvenor basis that we had described with
the G's? No.
Yeah.
We couldn't. So I really felt like the G epsilons in your paper should be the way to go, but we couldn't get we couldn't reduce Schubert's with those. We actually we rely, so your proof relies on the fundamentals satisfying a nice recursion, right? Our proof also relies on these forest polynomials satisfying a leaf labeled recursion, and then you recurse, and then you identify things that fall inside the quasisymmetric ideal. So we rely on your monomial basis, but not the G's.
So thank you very much. Let's thank the speaker again.